Hello future engineers, this is the second part of 2D rigid body equilibrium. So some of the problems here are still basic, but there are tricky problems. Calculate the force and moment reactions at the bolted base O of the overhead traffic signal assembly. Each traffic signal has a mass of 36 kilograms, while the masses of members OC and AC are 50 kilograms and 55 kilograms respectively. The mass center of member AC is at G. So let's put directly the weight 36 times 9.81 is 353.16. 36 kilograms times 9.81. So this is also 353.16. Then the mass of AC is 55 kilograms. The center of gravity is at G. So 55 times 9.81 is 539.55. And for this member OC here, it is 50 kilograms times 9.81, so 490.5. So we expect three reaction components at O, namely horizontal, vertical, and moment. So let's assume that moment should be clockwise. So first, R horizontal equals 0. Component of the horizontal reaction is 0, or resultant horizontal component of reaction 0. So OH is 0. So equals OH. So therefore OH is 0. Then R vertical equals 0. So you have O sub V upward. Then minus 353.16 minus 353.16 minus 539.55 minus 490.5. So O vertical component of reaction at O is 1736 newtons upward. Then finally, moment is 0 at any point. So let's choose O to be 0. So MO, clockwise positive. Then these are all counterclockwise. So 490.5 has no moment about O. It passes through O. So 353.16 times 5 plus 1 plus 4 is 10. Then plus 353.16 times 5 plus 539.55 times 4. So using your calculator there, MO is 7456 Newton meter clockwise. So the C bracket is supported at A, B, and C by rollers. Determine the reactions at the supports. The following are the given data. A is 0.9, B is 1.2 meters, theta 1 30 degrees, theta 2 20 degrees, and F is 200 newtons. So let's draw the free body diagram. Let's put the reactions here. Normal reaction at A, normal reaction at B through this point, normal reaction at C also through this point, and let's call that point O. So first, summation moment O equals 0 so that we can compute NA. So MO equals 0. Counterclockwise positive, so we have NA times A, then minus F times B. So those are the forces involved. Substituting values, 0 equals NA times 0.9 minus F 200 newtons times 1.2. So NA can now be solved. NA is equal to 266.7 newtons downward. Then R horizontal equals 0. And NB is positive. NB sine of theta 1. Then minus NC sine of theta 2, the horizontal component of NC. Substituting values, 0 equals NB sine of 30 degrees minus NC sine of theta 2, which is 20 degrees. Expressing N sub C in terms of N sub B, N sub C is sine 30 over sine 20. So N sub C is 1.462 NB. And finally, R vertical equals 0. The vertical component of NB is upward, so it is NB cosine of theta 1, which is 30 degrees, plus NC cosine of theta 2, NC cosine of 20 degrees, minus NA 266.7, minus F 200, replacing NC by 1.462 NB. So NB cosine 0 equals NB cosine 30 degrees plus 1.462 NB times cosine 20 degrees minus 466.7, combining these two. So NB is 466.7 divided by quantity cosine 30 plus 1.462 cosine 20. So NB is equal to 208.4 newtons up to the right, 30 degrees from the horizontal. And NC 1.462 of 208.4. So N sub C is 304.7 up to the left, 20 degrees from the horizontal, from the vertical rather. Determine the rope tension T for which the pulley will be in equilibrium. So this is the given figure. So we denote this as point O, and the reaction is only vertical because this is a smooth pin. Then let's call the vertical reaction as OV. But there's no moment at OV, so that's our equation, MO equals 0. Considering clockwise as positive, so it is T times radius 0.075 meter to be consistent. T is in newtons, radius meter. That's why you have plus 200 Newton meter. Then minus 2 kilonewtons, so this should be 2000 newtons times 0.12 meter. So from there we can solve T, 2000 times 0.12 minus 200 divided by 0.075. So T is 533.3 newtons. The maximum allowable value of each of the reactions is 180 newtons. Neglecting the weight of the beam, determine the range of the distance d for which the beam is safe. So remember, the maximum allowable reaction value of reaction is 180 newtons. So for minimum d, 50 should be closer to A, so that the reaction at B will be 180. And the reaction at A will be less than 180. So if this is 180, because 50 is closer to A, then 250 plus this is 300, so that means RA is 120 only and RB is 180 for minimum D. So this should be 180 and RA should be only 120. So if D is minimum or the 50 Newton load is close to A. So we set MA equals 0 because although we can find RA, we don't need to find RA as long as it is less than 180. It is 120 specifically. So 0 equals counterclockwise positive 50 times D. We're computing for the minimum D. Or 180 times summation moment A0. So counterclockwise positive. Let's begin with 180. 180 times 900 minus D, this moment arm, plus 50 times D, and minus 100 times quantity for 50 minus D, then minus 150 times 900, quantity 900 minus D. So computing the constant, 0 equals 180 times 900 minus 100 times 450 minus 150 times 900. That would be negative 18,000. Then negative 180D plus 50D, negative 130D. Plus 100D, 230D. 230D. Negative 180D plus 50D, negative 130D plus 100D, negative 30D, plus 150D, so 120D. So we can solve for minimum D. D is 150 mm. For maximum D, so 50 Newton load should be here, so that RA will be 180 and RB will be less than 180. So if the 50 load is somewhere here, then RA will be high and we limit it to 180. Then RB would be 120 only. So set RA equals 180 and RB will be less than 180, definitely 120. So since we know RA equals 180, then we set moment at B equals 0. So setting, considering clockwise positive, so RA 180 clockwise times this distance is 900 mm minus D again, and minus 50 times 900 and minus 100 times 450. So that would only be the equation because the moment arm of 150 is 0. So 180 times 900 minus 50 times 900 minus 100 times 450 is 72,000 and minus 180D. Solving for DD is 400 mm. Therefore, 150 mm is less than equal to D and D is less than equal to 400 mm. So that's the answer. So it's simple, but again, the trick is important to this problem. When the 0.05 kilogram body is in the position shown, the linear spring is stretched 10 mm. Determine the force P required to break contact at C. Complete solutions for part A, including the effects of the weight, and B, neglecting the weight. So if you look at the body, it is symmetric T. So the weight definitely acts on this web here. Just put it there. It is 0.05 kilogram times 9.81, so 0.4905 newtons. Then the tension in the spring is K times delta S, where K is 1,750 Newton per meter. And at this position, even if the P causes to break the contact at C, the spring is still stretched 10 mm at that case, or 0.01 meter. So these are the reaction components at O. Moment O is 0 because this is a smooth pin. So T is 1,750 times Newton per meter times 10 mm or 0.01 meters, so 17.5 newtons. So take note that when P causes to break contact at C, there will be no reaction at C because the contact is broken. So therefore, moment O is 0. And considering counterclockwise positive, so 0 equals P times 120 mm plus 0.4905 times 60 mm. And this is clockwise, so minus T, minus 17.5 times 40 mm. So we can now solve for P. P is 5.588 newtons. Then for the second part, neglecting the weight, so neglecting this, so just remove this part of the equation. MO is still 0, and equals P times 120 minus 17.5 times 40. So P is 5.833 newtons in that case. The 60 kilogram homogeneous disc is placed on a frictionless inclined surface and held in equilibrium by the horizontal force P and a couple C, where the couple is not shown on the figure. So find P and the couple. So let's draw the free body diagram first for the weight of the disc. 60 times 9.81 acting at the center here. So 588.6, use your calculator there, 60 times 9.81. Then we have normal reaction at this inclined surface, perpendicular to the inclined surface, and that passes through the center and makes an angle of 30 degrees with the vertical 30 degrees. So the couple should be clockwise because the moment of this normal reaction R and the weight about O is 0. So only the couple and P will have moment about O. That's our objective later. So since the moment of horizontal force P is counterclockwise, that's why the couple should be clockwise to counter the moment of B. That's it. First, to solve for P, we need to know R first. So that is the vertical component of the resultant should be 0. And that should be vertical component of resultant which is upward positive R cosine 30 degrees, then minus 588.6. So R can now be solved, 679.7 newtons. The horizontal component of the resultant must be 0 because the system is in equilibrium. And that is equal to P, positive rightward, minus the horizontal component of R, which is this, which is R sine of 30. So minus 679.7 sine of 30 degrees. So we can now solve for P. P is 339.8 newtons. And finally, moment O is 0. So R and the weight are not involved. They pass through O. Clockwise positive, so C equals C. And minus P times 0.3. Minus 339.8 times 0.3. So the couple is clockwise with a magnitude of 101.9 Newton meters. The 10-meter beam AB rests upon but is not attached to supports at C and D. Neglecting the weight of the beam, determine the range of values of P for which the beam will remain in equilibrium. So there are possibilities here. If P is too light, then this 20 kilonewton will cause overhang about C, no contact at C. So that's when P is light as possible. When P is maximum or heavy, that will cause overhang about D. So there's no contact at D. So it will surpass the 20 kilonewton load. So let's begin with the lightest P. So if P is light, this will this tends to go down and this will rise. So there's no contact here. So the only contact will be at D. So that's why we set MD 0 and take note there's no reaction here for minimum P. So MD is 0. Take note there's no contact here for minimum P because P is minimum. So the tendency is this will pivot about D and there's no contact about C. So considering counterclockwise positive, so 0, moment at D 0 equals P times 8 plus 4 times 3 and minus 20 times 2. So the reaction at D is not important because we set moment at D 0. And there's no reaction at C, of course. Solving for P minimum, P is 3.5 kilonewtons. Now for maximum P, there's contact at C, but no contact at D because P is heavy. So as a result, I will just exaggerate, it will overhang like that. So there's no contact at D. So moment at C should be 0 so that the reaction at C is not involved. So considering counterclockwise as positive again, P maximum times 2, then minus 4 times 3, then minus 20 times 8. So that's the equation. Take note, no reaction at D. Solving for P max is 86 kilonewtons. Therefore, The answer is 3.5 kilonewtons is less than equal to P less than equal to 86 kilonewtons. Determine the force magnitude P required to lift one end of the 250 kilogram crate with a lever dolly as shown. So that's the figure. Then considering the crate alone, so by symmetry, the reaction at A and B will be half of 250 kilograms times 9.81. So let's transmit it at A. 125, half of 250 times 9.81. So 125 times 9.81. When this dolly is about to lift the crate, then the reaction will only be in this wheel here. Then there will be no contact at the bottom of A here. So the reaction will be at the wheel only. Take note that the condition is the force P required to lift one end of that 250 kilogram dolly. So when the required to lift one end of the 250 crate with a lever dolly. So when the crate is about to be lifted, take note that they lose contact at A, because if it is not yet lifted, then there will be contact at A. When it is about to be lifted, there will be no contact at A. So that's the analysis. That's also the trick here. That must be understood, or else you wrongly solve this problem, even if it is simple for those who are really good at analyzing problems like this. So therefore, moment at the wheels should be 0. Considering counterclockwise positive, so it is P times 1500. Then this is clockwise, minus 125 times 9.81 times 275. So we can now solve for P. 125, 9.81, 275 over 15. And that is equal to 224.8 newtons. The mechanism shown is a modified Geneva drive. A constant velocity input produces a varying velocity output with periods of dual. The input torque is 120 Newton meter. For the position shown, compute the contact force at B and the magnitude of the reaction at A. Neglect friction and the weights of the components. So this is the input and that's the output. So this part of the mechanism of the components is inclined 18 degrees, and this one of the slot here inclined 28 degrees, and that's 180 mm. The input torque is 120 Newton meter, so be consistent. So we draw the normal reaction at B, normal to this 28 degree angle. And therefore there are two components, NB cosine of 28 degrees for the vertical, and for the horizontal, which is to the right, NB sine of 28. So I will not replace NB with the vertical and horizontal, we just analyze it. One is vertical, upward, the other is rightward. Then the reactions at A and B, horizontal and vertical. So the reaction at A is, if this is true, is up, down to the left, So it is expected to be NB also, the magnitude. Anyway, the horizontal distance between A and B is 180 cosine 18, but since this is Newton meter, let's make 180 in meter. 0.18 cosine of 18 degrees, and the vertical distance is 0.18 sine of 18 degrees, this one. So our equation is MA equals 0 because there's no moment about this pin here, although this is the input torque. That's the input torque, external torque. That's the internal reaction at A. There's no moment at A. Moment A is 0, considering counterclockwise positive. So the vertical component of NB is NB cosine 28 degrees and its moment arm is 0.18 cosine 18, this one, that one. Then the horizontal component is clockwise to the right, so clockwise. So minus NB sine of 28 and moment arm is 0.18 sine 18. So 0.18 sine 18, that's the moment arm. Minus the input torque 120. So that's consistent. NB is in newtons and the moment arm meter. And this is Newton meter also. So we can compute now NB 120 divided by quantity cosine 28 times 0.18 cosine 18 minus sine 28 times quantity 0.18 sine 18. So it's up to you to input this value in your calculator. You might wrongly input it. So the value of NB is 959.7 newtons. Then R horizontal is 0. So the horizontal component of the NB is rightward. So it is NB 959.7 sine of 28. Then minus EH. So we can solve EH 959.7 sine of 28. 450.6 newtons leftward. A vertical, so R vertical equals 0 also. Vertical component of the resultant. So NB cosine 28 is positive, 959.7 cosine of 28 degrees minus AV equals 0. So AV is equal to 847.4 newtons. Then the magnitude, we are only asked for the magnitude of the reaction at A. So that is square root of 450.6 square plus 847.4 square. So it is also equal to 959.7. So that's it for this problem. For the beam and loading shown, determine the range of the distance A for which the reaction at B does not exceed 100 pounds downward or 200 pounds upward. So take note of the condition. The reaction at B should not exceed 100 pounds downward or 200 pounds upward. So let's put the restrictions for the reactions. These are the restrictions. Then analyze which one will activate for minimum A and for maximum A, because we are asked for the range of the distance A. So if A is minimum, so A is small, so 300 should be closer here. So if it is closer here, there's tendency that A will go down, so it will push B upward. So this is the activated reaction, 100 pounds downward. If A is minimum, so that's the analysis. If 300 is closer to A, so the tendency is it will cause A to lower, so it will pivot about D, so it pushes B. So this is the activated reaction at B, 100 pounds. So let's consider minimum A first. So that is, we have reaction at D, of course. So we set, we don't want to solve for RD anymore, so we set MD equals 0 so that RD is not involved. So since we consider minimum A, so considering counterclockwise positive, so 0 equals 300 times, this distance is 8 minus A, then minus 50 times 4, minus 300 times, this distance is A plus 6 minus 8, 300 times quantity A plus 6 minus 8, or A minus 2, then minus 100 times 16. So simplifying, 0 equals 300 times 8 minus 50 times 4 minus 300 times negative 2 minus 100 times 16. So 0 equals 1,200. And for A, we have negative 300A and negative 300A. That's why we have negative 600A. So A can now be solved 2 inches. Now for minimum A, this one is minimum A. For maximum A, 300 should be closer to D, like this. So therefore, if it is closer to D, it has no tendency to lower A. So these loads at the right will cause the beam to touch the lower support at B. So the 200-pound reaction, which is upward, will activate for that case. If the 300, if A is maximum or the 300-pound force is closer to D, then these loads here will cause B to touch the lower support. So the 200 pounds will activate. So there's no 100 here. So therefore, considering counterclockwise positive again, so we set MD equals 0 again. And that is equal to 300 times 8 minus A. Then minus 50 times 4. Minus 300 times A minus 2. Just use this, then A minus 2. Then plus 200 times 16. So again, combining the constant, 300 times 8 minus 50 times 4 minus 300 times negative 2 plus 200 times 16. So 0 equals 6,000, and for A, negative 300A, and another negative 300A is negative 600A. So A is 10 inches. Therefore, the answer is 2 inches less than equal to A, less than equal to 10 inches. So that's it for this part 2.